Hi everyone. Today we would like to do our presentation on experiment 8, which is reflection and refraction. So I would like to introduce my group, Group 6. Abdullah Hazim bin Abdul Manaf, matrix number 229303, and Yagna Kumaran Alaki Tirnyana Selvan, matrix number 228823.
Thanks, Yagna. So let's begin with an introduction of our experiment today. First of all, the law of reflection states that when a ray of light reflects off a surface, the angle of incidence, the angle between the incoming ray and the normal to the surface, is equal to the angle of reflection, the angle between the reflected ray and the normal. The incident ray, the reflected ray, and the normal all lie in the same plane. This law applies to smooth reflective surfaces, such as mirrors. Next, Snell's law describes how light bends, refracts, when it passes from one medium to another with a different optical density, such as when light enters a denser medium, air to glass. It bends toward the normal, and when it enters a less dense medium, glass to air, it bends away from the normal. Additionally, total internal reflection, TIR, occurs when a light ray traveling from a denser medium to a less dense medium is completely reflected back into the denser medium instead of refracting into the less dense medium. This phenomenon happens under two conditions, which is the light must travel from a medium with a higher refractive index to one with a lower refractive index, and the angle of incidence must be greater than the critical angle, which is the minimum angle of incidence at which TIR occurs. Then ray propagation refers to the way light rays travel through a medium or across different media. It describes the direction and behavior of light as it moves. Moreover, for lens, the focal length is positive for converging lenses and negative for diverging. For mirrors, the focal length is positive for concave mirror and negative for convex mirror. The distance from the object to the lens-Rorschach mirror is called the object distance. It is positive if it is on the same side of the optical element as the incoming light. Otherwise, it is negative. The distance from the image to the lens-Rorschach mirror is called the image distance. It is positive if it is on the same side as the outgoing light. Otherwise, it is negative. The image is virtual if the sign is negative. The height of the image is positive if the image is upright and negative otherwise. Last but not least, the mirror equation or thin lens equation relates the object distance, image distance, and focal length of a mirror or lens. It is given as a picture aside, where f is the focal length of the mirror or lens, u is object distance, distance between the object and the mirror lens, v is image distance, distance between the image and the mirror lens. Magnification equation. The magnification of a mirror or lens describes how much larger or smaller the image is compared to the object. It is given as a picture aside, where m is magnification, h original is height of the image, hi is height of the object, v is image distance, u is object distance. Also, we can get some information from m value, which is if m greater than 1, the image is magnified, 0, 0, the image is upright, m less than 0, the image is inverted. So let's move to results and calculation part. From the experiment of Snell's law, we place a semicircular on white sheet paper so the ray passes through it. Then we mark the incident in transmitted rays up to 5 times. Here is the data and calculation of the Snell's law experiment. The first set, we get angle incidence was 20 degrees and angle refraction was 31 degrees. For the second set, we get 25 degrees for the incident and 40 degrees for refraction. For 3 repeated, we get 30 degrees incident and 50.5 degrees refraction. For fourth one, we get 35 degrees incident angle and 61 degrees refraction angle. For last one, we get 40 degrees incident and 76 degrees refraction. For index value, we calculated and determined that for set 1 is 1.51, set 2 is 1.52, set 3 is 1.53, 1.54, for set 4 is 1.52, and for set 5 is 1.51.
Moving on, for the experiment of total internal reflection, we will place a semicircle slab right angle triangle and an equilateral triangle on a white sheet paper, so the ray passes through it. Then we will measure the critical angle and also the percentage error for the critical angle we managed to get as our result. Here's the data and calculation of the total internal reflection experiment. The semicircular slab's critical angle is 47.5 degrees, right angle triangle's critical angle is 44.0 degrees, and equilateral triangle is 43.5 degrees critical angle. As it is given that the refractive index of acrylic is n equal to 1.5, we can use the critical angle formula to decide that the theoretical value of the critical angle is 41.81 degrees. Using the value, we can find the percentage difference. For the semicircular slabs, percentage difference is 13.61%. Right angles triangles percentage difference is 5.24%, and equilateral triangles percentage difference is 4.04%.
So, for the experiment of convex and concave mirror, we place a 5-slit former in front of the box light to form a parallel rays straight into the concave mirror so that the light is reflected towards the ray box. Then, by using a pencil, we trace the surface of the mirror in the incident and reflected rays. Additionally, by using a compass, we are able to draw a full circle that matches with a concave mirror so that we can measure the radius of curvature of the mirror. Lastly, we repeated the step by changing a concave mirror into a convex mirror. As we can see, here is the data and calculation we get from this experiment, which is for concave mirror, the focal length was 2.45 centimeters and radius of curvature 4.9 centimeters. For the convex mirror, we determined that the focal was 2.05 centimeters and radius of curvature was 4.1 centimeters.
Alright, for the last experiment convex and concave lens, it was quite similar to the experiment we did before, which is experiment 3, but this time we replaced the mirrors with lenses. We will place the convex lens and concave lens on a white sheet paper. As the ray passes through the lenses, we will trace the incident and transmitted rays. We will also record the focal length for the lenses. For convex lens, the focal length is 8.515 cm, and for the concave lens, the focal length is negative 7.95 cm. Why is that negative? That is because, as the concave lens diverges the light instead of converging, the focal length tends to be on the same side as the incoming light, which is designated as the negative side. So, after that, we will observe what happens when the concave and convex lens were placed together so that the ray passes through them, and observe the effect while moving them closer and away from each other. Moving into our discussion part. For experiment 1, due to the unavailability of the trapezoidal slab, we used a semicircular acrylic slab to perform the experiment, as both of them still have the same refractive index. For experiment 1, the refractive we calculated for each pair of the angles are precise and accurate with a theoretical value of n equal to 1.5. The average refractive index obtained is n equal to 1.52, which is within 1.3% error margin when compared to the theoretical value n equal to 1.5. Thus, the experiment successfully demonstrated Snell's law and accurately determined the refractive index of acrylic. For experiment 2, the measured critical angles for all sets show small deviations from the theoretical value of C equal to 41.8. The percentage difference for the semicircular slab is higher, which is 13.61% compared to the triangular prisms, which show smaller deviations, 5.24% for the right angle triangle and 4.04% for the equilateral triangle. Possible reason for this difference is measurements error, which is inaccuracies in marking or using the protector. For experiment 3, the experimental results confirms these relationships, with the radii of curvature calculated as 44.9 cm for the concave mirror and 4.10 cm for the convex mirror. Slight variations in the measured focal length, and radii could arise due to inaccuracies in tracing the rays, human error in measurements, or imperfections in the mirror surface. For experiment 4, the convex lens converged parallel rays to the single focal point, demonstrating its ability to focus light. The measured focal length of positive 8.15 cm indicates that it's a converging lens. The concave lens caused parallel rays to diverge, and extending these rays backwards reveals a virtual focal point. The focal length of negative 7.95 cm confirms its diverging nature. When the convex and concave lenses were nested together, the rays become parallel, indicating that the lens's focal length effectively cancelled each other out. When the lenses were separated, the distance between affected the behavior of the rays. Increasing the separation led to shifts in the focal points, and reversing the order of the lenses changed the orientation of the transmitted rays.
Moving into conclusion, for experiment 1, the calculated average refractive index of n equals 1.520 closely matches the theoretical value of n equals 1.5. The slight deviations can be attributed to experimental limitations, but overall, the experiment was successful in verifying the principles of refraction and determining the refractive index of acrylic. For experiment 2, the experiment successfully demonstrated total internal reflection and the measurement of critical angles for different geometries, where the percentage difference for the semicircular slab, right-angled triangle, and the equilateral triangle is 13.61%, 5.24%, and 4.04% respectively. The results align well with theoretical expectations for the refractive index of acrylic, with slight variations attributable to experimental conditions. For experiment 3, the experiment successfully verified the relationship between the focal length and the radius of curvature for concave and convex mirrors. The measured values align well with theoretical expectations, demonstrating the reflective properties of curved mirrors in their practical applications. The radii of curvature calculated as 4.90 centimeters for the concave mirror and 4.1 centimeters for the convex mirror. For experiment 4, the experiment demonstrated the distinct focusing properties of convex and concave lenses and their effects when combined. The results align with theoretical expectations, showcasing the principles of refraction in lens optics. The adjustable behavior of combined lenses emphasizes their versatility in optical systems. So that is the end of our presentation. Thank you to listening, really appreciate that.